Welcome to the short workshop on System C. We have a number of speakers today to talk about some different topics, HLS topics, and also some new things going on in functional coverage in System C, and with a little Accellera Working Group update from Martin Barnasconi. So we'll start with the first topic. He's going to talk about an overview of HLS. Please welcome Fred Doucette.
Thank you very much. This presentation is about high-level synthesis, and specifically high-level synthesis with System C. We use it for design with HLS. The thing that System C provides is higher level of abstraction. There's been thousands of tape out on a variety of design, from very small one to very large, or maybe 1,000 gate, 10,000 gate to 500,000 gate for a System C design, or maybe even more. Some very large processes, and System C is basically module with processes and things like that. Large data paths, mostly this is the bread and butter of HLS. Some control mix with the data paths on some larger system. And what's been demonstrated many times in the past is a significant productivity increase, which means the design gets done faster and it has less bugs, right? So isn't that fantastic? But what does this all mean? What is System C? How does it work? How is it different than RTL? That's actually the main question that most of the RTL guys would like to understand. So this presentation will try to answer those questions. So this is a picture which I try to distill high-level synthesis to 5 bullets. High-level synthesis transformed synthesizable C++/System C, so C++ for the computation and so on, System C for the design, into RTL Verilog. How does it do that? So first, it reads in the System C design. It reads in tech node spec. So what this is which technology library are we using? Are we using 14 nanometer slow corner? Are we using a 7 nanometer? What are we using exactly? Which corner? What clock frequency? What uncertainty? All these details are part of the tech node spec. The third input is synthesis directives. So when we write C++, specific C++ structure can get translated to many different kind of RTL implementation. So this here describes, for that particular piece of C++, this is what I want. So we need the C++ plus the synthesis directive to go through the HLS to get a circuit. So the synthesis directive in pair with the System C design. So HLS tool looks into the design, look at all the multipliers, adder, muxes, and things like that. Then it characterizes them at the node and the constraint we specify, meaning how fast is a multiplier for 12 bits, 14 bits, how slow can it be, and so on. Then it takes all the operations in the design and schedule them onto the available clock cycle. So it looks how many clock cycles there is to spread all this logic around. Then it generates RTL that's equivalent to the input. So here's an example. So what does it mean to describe computation with C++? So it mostly means write functions for data path, which we call data path functions. So here's an example. So this example at line 1 defines what we call a compute function. It takes 2 arguments, value and coefficients, and then it returns an integer. So all this operates on integers. Very simple, the code, it's a loop from 0 to 4. It multiplies the values by the coefficient and accumulate them into sum and return sum. Looks familiar, doesn't it? So this kind of code can describe DSP processing, image processing, all kind of transformations, and we can write it broadly like this. So when the tool reads this code, what it sees, well, okay, I start initializing sum to 0, I initialize the I to 0, I enter a loop, I keep iterating and multiplying and adding the values into sum, and when I is greater than 4, I'm done, I'm returning this. So HLS tool, when it first reads the code, it sees this as a loop. So, but what does this loop mean in hardware? What does this mean in hardware is the question that System C answers. So at the first level, there are things to specify module, port, signal, processes, clocks, reset, things that we usually do in Verilog explicitly. Here's a module, here are all the ports, all the clocks. All of this can be done in C++ using the System C classes. So System C modules provide the I/O interface of the design, the specification of the clocks and the reset. It basically describes the structure. So here's the top level module, here are the sub-modules, here's how they're connected together, and so on. SystemC process defines the I/O behavior around the calls to the DevPath function. And I have an example for this. So basically, SystemC process specifies the control flow. It's usually an implicit FSM, but not all the time. And the SystemC processes is what gets concretized by the HLS tool. So HLS tool takes SystemC processes, translates them in Verilog, and it does the scheduling, moves the operation around. So let's take a look at a SystemC module. This is what it looks like. So this is legal C++ syntax. Here you see SC. Every time you see SC means SystemC. So SystemC module DUT, here's a port for the clock that you can see here, port for reset, Boolean type, so 1 bit, 16-bit unsigned integer, so SCU in 16 values, an array of n. So n here is from 0 to 3. The input coefficient, one output valid out. The sum out is also 16-bit. Here's the definition of a process, and we'll go into what the process looks like. So here's a process in the context of SystemC. So that function I show you is now here in blue. It takes the values and the coefficient, but the values and the coefficient are coming from the input port. So it samples the valid input, stores that in a Boolean variable, samples all the value and the coefficient from the port, calls the function, write valid out. If it's 1, it's going to write 1 here, otherwise it's going to write 0, and then it writes out the sum, wait for the clock. So each time you see a wait, it waits for the clock. So here there's one wait, it's in this loop, it reads everything, writes the output. Read everything, writes the output. Read everything, writes the output. Everything before the while here is called what we call reset. So if you look here, it initializes the valid output, wait for the clock, and then it enters this loop, and then it's going to be here forever. So this is the same diagram I showed you earlier. This is the loop from 0 to 3 where the filter function is. So we can run this in C++ and actually get some waveforms. So with this code and a little bit more code to say, give me the waveform, we can see something like this. Valid goes up, all the values for the filters are here, the coefficients are here, the output comes out at the next cycle. So with this code, we can start seeing waveform. If I have a lot of modules, I can start seeing the interaction between all the modules, and I can get a sense of whether my I/O protocol works well or not, and I can build a system like this. So now, what do we do with this? Going back to the function, we need to tell the HLS tool how to transform the C++ code into a hardware structure. So C++ code can take different meaning in hardware. And the most fundamental example is a loop. So what do we do with this loop here? What does that mean? So if we think about this, it's a filter. We could use 4 cycles to accumulate the sum, doing 1 multiplication every cycle, or we can unroll the loop, and all the iteration will be executed in parallel. That's what happens. If we unroll the loop, then you can see the 0 here, the 1, iteration 1, iteration 2. So you can see a nice adder chain here. So if we unroll the loop, we're going to get this structure like this. What's in green here is called a synthesis directive. So it's something that has meaning only for the HLS tool. It has no meaning for when we write the C++. And what it does, it tells the tool this is going to be a data path, or at least this is going to be a structure like this. And since all the variable index are constants, there is no muxing around this. So the SystemC plus the synthesis directive is what we call a hardware model that's ready for HLS. There's 2 directives that goes with this description. Is first, unroll the loop, and second, balance the expression. So you can see here, we don't have a chain of adders anymore. We have a tree of adders. So that's a little bit better for timing. And HLS tool can try to do something here with CSAs and things like this. So once we have this, we're ready to synthesize it. I mentioned about the TechNote setup earlier. The constraints, unroll loop, balance expression, clock period 0.7. I want a design that's cycle accurate, meaning the RTL I/O behaves exactly the same as the SystemC I/O. So when I look at the SystemC waveform, I look at the generated RTL waveform, same exact thing. How does it do this? I showed you this slide earlier. Now we're at the 3rd bullet. So what it will do, it will characterize all the resources for all operation. So let's see exactly what this means. So looking at this, what do we have? We have 16-bit multipliers here. We have some adders here, 16-bit adders. We might have some mux, 4, 16 to 1, and we have registers. So what the HLS tool is going to look at all these resources and characterize them for, let's say, a fast version and a slow version. There's many ways to do that, but one way to do this is to go to logic synthesis and say, tell me how fast this thing is, or to do some interpolation or somewhere, tell me how slow this thing is. So for this particular example, which is of course a cooked up example for the slides, the delay of the fast resource is 0.27, the area is 70. The delay of the slow multiplier is 0.5, area smaller, 36. So you can see fast resource faster but bigger, this one slower but slimmer. Same thing for the other resource. So the adder, slow adder, fast adder, slow adder, fast mux, slow mux. Register, there's not a lot of difference here. So the tool knows how fast and slow everything is. So with that, what it can do is can try to build a schedule. So you can see here on the right side, there's 0.7 cycle time. So if we put a slow adder followed by a slow multiplier, it's not going to work. So we need to go back. Slow adder followed by slow multiplier followed by fast adder, not going to work. So we need fast, 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 mux, register, boom, it fits in the cycle. So HLS tool tried all the combination of fast and slow, and it can go in between and see how much logic it can pack in a cycle. And this is what we get. 4 fast multiplier, 3 fast adder, the area is 335, the delay is 0.56. So with that, we can generate RTL, simulate it, and this is great. However, what's great with HLS is we can try something different. Say, okay, let's try a little variation on this and see what happens. And this is really where some of the power is coming from. So instead of cycle accurate, I want the smallest design possible. So unroll the loops, balance the expression, minimize the area. So the idea here is increase the latency to reduce the area of the design. So what the tool can do is add some states. So instead of doing everything in one shot, take 4 states to do it, or 4 clock cycles to do it. So by taking 4 clock cycles, it can take the multiplication and the addition and spread them over these 4 clock cycles. So it adds latency, but it reduces the number of resources by sharing the resources. So it can share the multiplier and the adders. So what we get is something like this. This looks completely different. So now what we have is sharing muxes. So we only have one multiplier, but we have sharing muxes in front of the multiplier. We have some register to register the values for 1, 2, and 3, the index in the incoming array. We have the same thing on the coefficient. So the first one goes to the multiplier. Then the output gets registered. And then the second one, the mux open here. Then share this guy to store the output, and so on and so forth. And then the state machine to control all these muxes when they open and close is all generated automatically. So the area of this is 139. So it's roughly 1/3. But the throughput is 5 clocks instead of 1 clock. So you can see that there's a trade-off here. And depending on what the design is, we can afford this trade-off or not. So one other thing that you might have noticed is that the coefficients here are constant, and we register them. So we can tell the HLS tool, don't register stable inputs. Which inputs are stable? Coefficients. This here's another about 20% area reduction. Now we get this guy. So this gets muxed, the right coefficient gets muxed into the multiplier, and so on and so forth, and we're at 115. Finally, the bread and butter of HLS, pipeline it. So when we pipeline it, it means the scheduler in the HLS tool will insert registers between the resources here. And in this case, we'll get 2 banks of register before the output, and we'll be able to use slow resources because we have enough clock cycle, and we'll also be able to have a nice CSA on this side of the filter. So the area of the pipeline version is about maybe in the middle between the min area and cycle accurate, but the throughput is 1 with a latency of 2. So this is a very small example. So using this on a large design, you can see the kind of things the scheduler can do, the kind of change it can do in the generated structure. So it recomputes the FSM, it reallocates the sharing muxes, and it keeps track, it makes sure to open up all these mux in the right cycle. So this is what abstraction means. What's abstracted in System C compared to our RTL design is the following 3 things. First, operation to resource bindings and sharing muxes. So when we write a System C, we look at operations that are to be mapped to resources. Multiplication versus multiplier, addition versus adders. So all these operations, they're moved around the input graph, and resources are allocated, and the number of cycles can change in order to minimize the resources based on the constraints. So that's the first thing. The second thing is the registers themselves, they don't need to be specified in the SystemC code. So we don't need to specify which cycle exactly the operations happen. We don't need to specify what can be registered when. So if I take 2 cycles, I need to register the input between cycle 1 and cycle 2. But this is a decision of the HLS tool to do 2 cycles. So we will go and add the necessary register in order not to lose these values. And the third thing is the creation of the FSM and the transitions between the states of the FSM. So there are wait statements in the code. The wait statement gets created to FSM states, and based on these transitions, the write mux open for the sharing muxes, and the write enable, the enable to the register get activated at the right time, and the current and next state logic is generated by the tool. So these are a lot of details. And when we do a change on NRTL, there's a lot of things that we need to think about and we need to change, and it's very error prone. But the HLS tool takes care of this for us. So this is what the abstraction means. Small disclaimer at the end. It does not turn random software into hardware. So it doesn't mean because in C++ that it's going to take any C++ and create RTL. We still need to design the thing properly, but by keeping in mind what abstraction means and what the tool does with this abstraction, we're able to write SystemC code and get very good circuit that will typically beat the NRTL implementation. So this is the key message here. All right, so what are the benefits of HLS? Because many of these details are abstracted out, fast design turnaround. So we can rescale a pipeline, say go from 200 to 250 stages, rework the sharing logic very quickly by turning on a switch. We can add some branches or add some states, and it's very fast to regenerate this. So we can quickly implement microarchitecture, but we can also regenerate it and do some optimization for area, some optimization for power, and let the tool explore all these different things and find out which one is the best one, or at least the one that's the best for tape out. High-level verification. So I didn't mention that yet, but this is also a huge productivity benefit. So there's huge benefit to verifying close coverage at the SystemC level. Basically, these compute functions have the verification of input and output correctness, bit match the algorithm model with this. And once we're able to bit match the compute function, the bugs are mostly integration bugs. So this HLS block with this RTL block, is it programmed correctly? Are the inputs sent in the right cycle? These kind of things. Not overflows, not mismatches in the arithmetic. And so with these 2 things, enable us to get to the finish line faster and also to have lower bug rate than NRTL implementation. So Accellera SystemC standardization, which is the umbrella of this conference. So the Accellera group is a fantastic place to have discussion about SystemC and HLS and the SystemC work group. So this is very energizing and exciting place. Further work on standardization, so channel libraries would be great to have this in the standard, point-to-point memories and things like that. And the synthesis directive. So how do I specify I want to unroll a loop, I want to pipeline something? These are great things that if they're standard, it will help us energize the marketplace beyond the energy there is now. So. And also C++11 and C++14 for when we work with the algorithm guys who are more sophisticated programmer than the design guys.
Our next speaker is Mike Meredith from Cadence, and he's going to talk about structuring models for synthesis and corresponding data types.
So SystemC models have lots of purposes. One of the interesting things about SystemC is that it can be used for lots of purposes, from abstract system models down to writing RTL, down to analog stuff. So I mean, it has lots of different purposes. Some of the main purposes are virtual platform modeling, high-level synthesis, and verification. The way that you model for these purposes is a little different depending on what purpose you're aiming towards. Indeed, quite different depending on what purpose you're aiming for. The TLM modeling for virtual platform work, the goal is the minimum amount of detail that is enough to represent the behavior as it appears at the registers the processor can see, and simulating as fast as possible. So A lot of techniques are used to use event sensitivity, abstract communications through function calls, passing pointers to host memory. As an HLS guy, I look at this and I think, man, these guys are cheating. They are cheating every way they can to get high simulation speed. And for their purpose to have the appropriate level of detail, the algorithm is correct, the memory map is correct, the transaction order is correct, yeah, you can remove a lot of levels of detail. If you are going to model for synthesis, you kind of have to bring that high fly and abstract model down to earth a little bit. And the appropriate scope for this is not really probably full system. You're going to be implementing one block at a time, 5 blocks in a subsystem, 5 subsystems into a bigger subsystem. And the appropriate level of detail is cycle accurate for protocol and control. You're going to have to tell in the model, when do we drive this pin and when do we drive that pin? And that's a lot more detail at the communication level than is required for virtual platform work. But you can and should maintain as much abstraction in the algorithm as possible. And that's a lot. As it turns out, you can maintain quite a lot of abstraction in the algorithm part of that. So the techniques that are used, you have clocks. Virtual platform guys don't like clocks. Any virtual platform guys here? I saw hands. You guys hate clocks. I know this to be true. Because clocks slow you down every time. They tick all the time. And they slow your simulations down. They have to do things every time the clock ticks. It's terribly painful. For an implementation model where we're going to handshake data on the clock edges, we have to have that level of detail. We have concrete communications using pin-level protocols, detailed modeling of the reset behavior. The virtual platform guys largely, for some of their uses at least, can ignore the reset behavior and just assume that the system comes up ready to go. Whereas for implementation, you have to be able to tell, have I gotten a power on reset? I need to reset these things. Have I just gotten a reset, a soft reset from the processor? I need to reset a different set of things. So I have to be able to model that and simulate through that to make sure I've got it right. And again, to maintain abstract modeling of the algorithm and abstract modeling of the storage architecture. So modeling for verification, the appropriate techniques are verification techniques. And I see this done using System Verilog as a verification language and using SystemC as a verification language, depending on the preference of the user primarily. But in any case, you're going to be using verification techniques. Model structure, Fred went over this. The critical elements I'll go over. Again, you have to have a clock and a reset. You have to have pin level, SC in and SC out. That's 1-bit input or a 9-bit input pin modeled at the signal level. You can have submodules and submodule connectivity, same as you would do in Verilog. You can have multiple threads and methods, multiple different processes. We'll talk about those briefly. And you can have communication between the processes inside. And we'll talk about what those process types are. So there are 3. Clock threads, and SC methods. Clock threads and threads for a synthesis purpose are pretty interchangeable. That's because threads are more flexible than clock threads. And for synthesis purposes, we have said, as long as you constrain the thread to the same limitations that the clock thread has, then we can synthesize it. Because fundamentally, the synthesis tools need the semantics of clock threads. So I'll talk about the semantics of clock threads. At the start of simulation, each thread and clock thread function is called. It runs until it hits a wait, and then it returns, this is at simulation time, returns the control back to the simulator. And then other threads can begin and do their reset behaviors. When it returns from that wait, and after each wait, it looks at the reset condition. If the reset is false, it continues execution and does the rest of its coding. If the reset condition is true, then in simulation, the stack is torn down and the function starts again and it does the reset behavior again. So that's how, in the simulation, we model reset behavior in threads and clock threads. This means that everything before the first wait in a thread function is going to be reset, is reset behavior. For synthesis, same semantics. Everything before the first wait is reset behavior, but it's not a pull something down from a stack. It's a interpret these behaviors before the first wait and implement them as resets and sets on flip-flops. So it ends up being all the reset behavior has the effect of setting up resets on flops. So in the reset behavior, you put in assignments to output ports, assignments to signals that are used that you're writing to for communication between threads, and assignments to variables. To the extent that those variables end up being implemented as registers, those registers end up getting this reset behavior. And I blew over the fact that modules can have storage and functions. And so the storage, these are data members of the modules. Those would include the structural stuff, port signals, data members, submodules, connectivity. Also, the initialization of those variables that are part of the module class. It's important that those be done inside the behavior of some process so that they get executed by somebody when reset occurs, as opposed to a common practice in C++ and in virtual platform modeling sometimes is to initialize the storage that is the state of a module in the constructor of the module. But if you do that, then that doesn't execute when reset occurs, so you need to initialize storage in the reset of some module or of some thread. So the three types: clock threads, threads, and SC methods. This is a clock synchronous thread process, can have waits that wait for the next clock edge. So for each clock thread, you give a clock and a sensitivity, sensitive to the positive edge of the clock or the negative edge of the clock. And then when you say wait, the model will wait for the next sensitive edge of the clock of that process. This gets implemented in the RTL as an FSM. If you're thinking about breaking up your design into multiple threads or multiple modules, but into multiple threads, think of each thread as an independent FSM that's going to be cooperating through some signals and communication. And so if it makes sense for some purpose like rate management to have two FSMs, then you want to implement that as two threads. SC thread, equivalent to SCC thread. The SystemC semantics for SC thread are more broad, more expansive, and more inclusive in terms of what it can do. It can wait for things that are not clock edges. But if you do that, we can't synthesize it. So for a synthesis purpose, you can use threads, but only if you limit them to be equivalent to clock threads. Finally, SC methods. This is very simple. An SC method is a Verilog always block. Almost exactly the semantics of a Verilog always block. You might think that the people who wrote the original SystemC standard looked at the Verilog spec before they created this construct. And you can write those, and they are synthesizable. And if you were to write a model that was all SC methods, and I've seen it done, you're writing an RTL. And doing that in SystemC is probably silly. There might be some corner case where that's a good idea. But there's a perfectly good Verilog tool set and flow for that. Probably that would be a better idea. But it turns out to be quite useful to be able to have an abstract definition of your FSMs as an implicit state machine in clock threads, and a little bit of RTL around the edges to do some of the I/O for you, to give you a asynchronous bypass path, stuff like that. Having a little bit of RTL around the edges of your more abstract model turns out to be quite handy. And so you can combine, and a lot of models do combine clock threads and SC methods. Data types, I won't spend much time here. All the C++ integer data types, except for wchar t, which I bet you haven't used a lot of times, are supported. The synthesis standard does define some refinements over the C++ standard. It defines that it shall be a 2's complement signed representation. That's actually not, you can create a C compiler that implements numbers without 2's complement. A lot of programs won't work, but it's legal C. And in order to be able to predict what you're going to get in the hardware, the synthesis standard defines specific bit widths for the C++ data types. SystemC data types, there are a few that are of interest. scint and scuint are for specific bit widths, so I can have an 8-bit unsigned variable. It will behave properly when I add 1 to the value 255. And these are limited precision and limited width. They only work up to 64 bits. There is another data type which will have arbitrary bit widths. There are good purposes in hardware for a 3,000 bit vector, a 3,000 bit variable, and those can be modeled and synthesized. Fixed point, these are for modeling fixed point data, 8 bits to the left of the decimal point and 5 bits to the right of the decimal point, and have saturation and rounding behaviors built in so that you don't have to do shifting and adding to do that kind of math. SCBV and SCLV are included in the synthesizable subset, and the way they're included, they don't add anything. You should forget about them. SCBV doesn't add anything to what SCBigUint does. Semantics, the semantics are about the same, but it doesn't have arithmetic support. SCLV is a 4-state logic, 0, 1, X, and Z, but for the synthesizable subset, you can't use X and Z, so I'm going to say forget about that as well. The ones that you'll use and should focus on are scint and scuint, scbigint and scbiguint, scfixed and scufixed. And the C++ types have a place as well.
Our next speaker is Bob Condon from Intel, and he's going to talk about real-life HLS and using it in the real world and his experience with that.
So at Intel, we have many teams that have used HLS in production, both for algorithmic-dominated designs and control-dominated designs. And now we've got people who've done this for many generations, and they've taken a design from one discipline, and that group has been canceled, and they've moved it to another one. The key benefit that the happy customers see, and not all customers are happy, but the happy ones, they have two things that they'll say. They get their design to market faster because they find bugs sooner, and they can tolerate a late-breaking architectural change. And we get a lot of those. So I'm going to talk a little bit more about what we've learned in designs that have gone through several iterations. Originally, we thought that one of the benefits of HLS is when you have a new target technology, if you're going from 14 nanometer to 10 nanometer, the tool will handle that for you. And that's true. That works out, and we migrate designs that way. But we're finding in the power domain that a lot of times sticking in the same technology node but worrying about power is almost like going to a new target technology. And we have designs now so some HLS tools will take into account some aspects of power when they're doing scheduling. They will try and schedule to minimize how much change goes on any given clock cycle. But we have a bunch of designs that we've worked on in the past year that static power is important too, because this circuit's going to get turned off a long time and then turned on only when we need it. So we wanted to really do a mix of low leakage cells and regular cells, and that's not really supported in the tool. And we also found our architects, their best guess, and this is a little bit sketchy. So I work with a lot of architects who can tell me within 5% what they expect a small design is for whatever they've designed. But they really have no idea up front what the power is going to be right now. But what we did find out is that we could very quickly iterate through a number of similar designs where we just changed the latency. Then we ran these designs completely through our RTL flow, our static power flow, and our dynamic power flow. And in about a day, we could give the architect a menu of here are 5 or 6 choices. So effectively, if you can quickly generate RTL solutions, you can get good answers for whatever problem you're trying to solve, even if the tool itself doesn't support it directly. The other key thing to make HLS successful is you want to find bugs as soon as possible, and that really means reusing tests from other parts of your world. This is a little bit hard in Intel because we'll have an algorithm design team, might be in Israel or Germany. The implementation will be done, the HLS implementation will be done on the West Coast US, and then the final RTL validation is going to be done in Bangalore. That's a very common pattern in my world. The goal with any testing is, well, if you have something that fails, you have triage to do. So you got to figure, is the test wrong? Did two people interpret the spec wrong? Or is my design wrong? And it can be any of those. So you want to find as many failures as possible with the cheapest test in your arsenal. And the cheapest test in an HLS flow is testing whatever you can before you actually run high-level synthesis. You want to flesh out all the functional bugs, all the saturation bugs. So some of the patterns that we use, we have people who design algorithms in MATLAB. They dump vectors for us, input and output vectors, and we use those in the high-level synthesis design. Most of our initial high-level synthesis designers are Verilog coders. They're not necessarily good C++ coders out of the box. So we always provide them with someone who can write a decent parser, in this case a MATLAB parser, or some people will include the MATLAB code directly in the SystemC model. You can do that as well. But doing so keeps the algorithm and the implementation in sync. If there's a bug, it's not a functional bug, it's not a saturation bug. It's a bug that's caused by timing handshakes. And if we know that, then we know where to look if we get a failure later on. Some HLS models themselves are fast enough to integrate directly into a virtual platform model. And we do this somewhat regularly. Sometimes with a little bit of hackery, we turn off the clock on the HLS model when it's not needed. And that lets us run a faster simulation. And then we have another set of designs where we'll have a good an OVM or UVM test bench on a design that we're going to make a lot of changes on. So a lot of our bus fabrics, we have a large OVM or UVM test bench. And when we're converting to SystemC, we run the SystemC model against the OVM, UVM test bench to make sure the SystemC implementers understood what they were building. Designs change over time. The initial design from an RTL coder is going to be at a low level. So we've adopted the software practice of refactoring. Refactoring is changing a design without changing its functionality. So changing it to make it easier to edit, to maintain over the long run. And to do this, you need decent unit tests somewhere. A 1-minute C++ unit test will test a lot of functionality in a design. It's fast enough to run every time you do a compile. It's, in our case, we build it into the make step. But if you do that, then you can start refactoring your designs. And one of the things that we do a lot is we'll templatize our data types and our modules so that we can reuse them in many different situations with many different bit widths. We also will go through a step of separating the control from the algorithm. I'll show that on the next slide. And then we'll add debugging to our modules. So here's a function. This is what the original code looked like. This is a tiny, simple function. It really looks, this came almost verbatim out of the algorithmic model someone wrote. The spec specified that it should be implemented with this kind of rounding. So the architect doing the data width specific set gave us roundings that work for his algorithm. Turns out if you implement it exactly like this, you'll get a bigger design than you need because it ends up doing rounding on each step. And this final version is a Q of R result, a design which will give you better Q of R. If we take all three of those together, and we actually keep all three of those versions in the code because it's easier to debug. So if the algorithm changes, we first want to make sure that that one that looked like the algorithm code still works. And so we ended up creating a tiny test bench in our design that we may not compile every time that takes a template and will run one of the three different functions there. In some sense, we're doing extra work. We're maintaining three separate functions, but this makes debug easier. Another common pattern is separating control from functionality. So we have this circuit takes in 8 samples per cycle. It produces 8 outputs per cycle, but each output needs more than one input sample. Each output needs 4 input samples. So essentially, we want to build a little shift register where we get 8 live cycles and consume maybe 3 or 4 that we received the last time around. So this is something that a lot of times if you're going from the time domain to the frequency domain, this is a very common pattern. We can build a class in C++ that handles all the details of this. So we have a time domain window. It has a reset function. It implements the square bracket operator. So users of this class can refer to things in the square bracket operator. And all it implements is a shift register. There's no magic here, but it's templatized with the number of inputs per cycle, the number of inputs needed for each function to compute, and the data type that it's going to operate on. And if you're willing to do that little bit of work, then we have a design that, in the overall design that this is part of, there are 30 different submodules that look verbatim like this. The control part is here. We read the inputs into the shift register, and then we call whatever function we're calculating on. So we'll have many functions like this, and they will look pretty much like they did in the algorithmic code. And these functions may actually be shared with the algorithmic model. So we have controls separated from design. And any fixes, improvements we do in the control, any debugging, we get to reuse. And any HLS constraints. And down here, we can still use that square bracket operator. It's no longer really an array operator, but has the same effect. It's implemented from our shift register. Repurpose C++ tools. Once every 2 months, have someone go review what's new in C++ land. Some of the ones that we use, we do much of our designs in Eclipse. We've added some support for the systemc data types so you can debug them and see what they actually look like. We use lots of templates in our code, and this is handy for navigating new code if you have a chunk of code that you're not familiar with. We use Google tests for regression tests of C++ libraries. Our Verilog coders aren't really good at writing a command line parser, so we steal the one from Boost. And we steal a lot of Boost metaprogramming idioms that we have repurposed. Recap, the biggest benefit is you can generate lots of different RTL solutions quickly, and that lets you fill a lot of holes in your environment. Reuse every test you can from either the architectural functional world or from the RTL turn-in model. Spend some time refactoring code to make it reusable in other circumstances and easier to debug. Separate data path from control and reuse those separately. And then see what you can steal from the C++ software engineering world.
All right, our next speaker is Dragos Dospinescu, who's from AMIQ, and he's going to talk about some work that he's been doing on functional coverage in systemc. A little bit shift from HLS, but I think an interesting topic.
Hello, my name is Dragos Dospinescu, and I work as a consultant, as a verifier for AMIQ, and I mainly work with verification and the systemc modeling. I'm also the author of this library, and I worked in conjunction with one of my colleagues, and I will be talking about functional coverage for systemc. So first of all, I would like to begin with the motivation for this, why we need functional coverage, then what actually is functional coverage and how functional coverage for systemc works, how it is related to functional coverage, and what are the basic features that it provides. And then we'll take a look into more details regarding different coverage constructs, coverage control functionality, database management, and I will, after that, conclude with some key points illustrated during this presentation, and then I'll show our plans for the future. So first of all, what is the primary motivation for functional coverage in systemc? One of the most important things in order to develop constrained random test benches is functional coverage, alongside with constrained random generation, which we already have, and of course, systemc, UVM systemc. And related to this, it's the fact that we need to measure in a way how random our test cases are. So next, we also have the possibility to define milestones in our project based on some concrete notion that tells us what kind of functionality we have tested. And we can also track the verification progress during the development cycle, so we know at each step what is our current status. And also one good motivation for this is to generate reports on what functionality was tested in our model. So at the end, you will see what the features are and how thoroughly they have been tested. You will be able to see that by generating some reports over the coverage that you have defined. So functional coverage, basically it's a notion that tells us what kind of functionality we have tested. This is what I mean by records what happens during test execution. It's a metric that is used in constrained random test benches. And what happens can be anything. It basically depends on what the verification engineer or the systemc model architect would think of. can be everything from basic scenarios or complex scenarios down to bus level data and control paths, stuff like that. And it's also a metric that tells us how much we have verified in our model. So we can see at any point in time what part of functionality we have tested and what not. And I think it's best to illustrate this on a simple example. So here we have a simple module that can divide two integers. And it has two inputs, basically. So it has the input A and B, which are both 64-bit. And it has one output for the division of the two integers. And then it also has another output for error whenever we try to divide by 0. And as you can see, because we have inputs on 64 bits, it's obvious that the input space is huge, so it cannot be verified exhaustively. So what would be the functional approach to verify this kind of module? We will try to think of scenarios or interesting cases. Regarding that, we would look at the inputs most of the part and also at the outputs. And for the inputs, probably the most interesting cases would be values like 0 and 1 and minimum and maximum. And also something in between, because in constraint random verification, we would like to see what happens with some random values, not just the values that we think we will be using, because this way we achieve a verification space that it's more broad, so we might catch bugs that we didn't think of. Also, we could think about relationship between A and B. So what is the parity between them? Is one odd and one even, because we are dividing integers, so the remainder will get truncated, or maybe the sign. So these are just some simple examples. We can think of more, but this is not the complete list. I was just giving you the basic idea. And what's important to note here is that the coverage is based on the model's features. So the difference between functional coverage and code coverage is that the functional coverage is written by somebody, and we have to keep in mind the intention of the model or the intention of the RTL. It doesn't really matter. We have a block, we have to verify it. We think of the features that we want to see in it, and then we write some coverage for that. And in the case of code coverage, we will not be able to catch problems related to functionality which is missing, because the code is actually can be seen as being executed, but some feature might be missing. So then how does this all relate to functional coverage for SystemC? What is this library? Well, it's a C++11 library that is header only, and it does not rely on any other library. It's also under the Apache 2.0 license, so it's free to use, and you can use it without any charges. And the purpose of this library is to provide functional coverage capabilities. What this means, I'll explain in the next slide. But the most important part here is that it is based on the System Verilog standard. And we picked this standard as reference for multiple reasons, one of them being that we already know that the System Verilog provides a functional coverage model, that it's working. And a lot of people are already accustomed to this, so the transition will be easier in this case. So to use the library, you simply download it from the GitHub repository, and then you can include it in your project, and you are set to go. So as an overview of what the library is able to do is it provides you all the things that you need in order to define a complete coverage model. And these are the definition concepts for the coverage model is the bin, the cover point, cross, and cover group. And I'll explain them in more detail later. And then we have some coverage control functionalities, which you can use to adjust your coverage numbers or disable sampling. We'll look at that also. And then we also have interrogation of the coverage database during runtime to check during the test execution, not only when you have the results, what is the status of my coverage. Also, various functionality involving coverage database management that we will look at in the next slides. Bin is the most basic coverage construct. Yeah, before I go into explanation here, the reason for why we have this comparison between System Verilog and functional coverage for SystemC library is to see that the code is actually pretty similar. So I'll only focus on the left part in explaining, but the purpose is to see that they are equivalent in a sense. And bin is basically just a collection of values and intervals that are of interest to the user. And these values will be dependent on the intention of the verifier or the SystemC model architect. And to define a bin, you will have to use the bin class parameterized by the type of data it will contain. And then you specify a name as a string, and then you can list how many values or intervals in session. So you are not constrained with regards to the number of arguments here. And there are multiple beans that each have different purpose, and I'll explain all of them. So the regular bean, which I just showed you, is intended for covering data, or better said, is intended for actually registering data that you want to see in your tests. And the next one is similar in a way, but it's used to split an interval into multiple bins. So in this case, if we have the interval from 0 to 255, then instead of having one bin which contains the whole interval, I would like to have 3 bins which divide this interval into equal slices. And this way, we use the bin array construct to achieve that. And then we have illegal bin, which is in a way the same. So they are all similar to each other, but this one is intended for data that we want to see that it never actually happens during the simulation. So if this happens, if we see that this bin is eventually hit, and I will explain what that means later, will trigger a problem, and this will be caught by the library, and it will throw an error, basically. And the last one is the ignore bin, and this one is intended for ignoring data that you are not interested in, basically. Here I wanted to show a cool example of the usage of bin array. And the purpose here is, with regards to bin definition, the only problem that I see with how you need to define the bins is that you have to specify the value at compile time. So we have gotten some requests from users in order to be able to construct bins based on some function or some algorithm that will be able to get the values from that. And here it's a simple example with a function that returns us the first n integers from the Fibonacci sequence numbers. And we want to get a bin for each value here. So we have this function, which is a lambda function, but it doesn't have to be. It's just an example. And then we instantiate the bin array with the function which receives the number of values to be inserted into the vector that is returned. And then this bin array will actually split the vector into multiple bins. And as we can see here, we have one bin for each value in the consecutive numbers of the Fibonacci sequence. The next coverage construct is the cover point. And here, the cover point is the construct that tells us what we are actually sampling. So what this means is, we have seen before the bin is holding the data, but we don't know what it represents. For that, we need a cover point. And the cover point, it's a construct that contains multiple bins, registering the data that we want to see. And then it ties that to a variable that will get sampled. And that variable has some meaning. So in this case, the variable is called data, and this could be some data got from the bus, or it could be a simple flag which tells us whether a certain scenario was triggered or not. So to define a cover point, you will use the cover point macro, and then you have the type of data that you want to sample on, and then the name of the cover point, and then the variable that will be sampled. And following that, you have the list of bins that will be included in the cover point. And these bins don't have to follow any rule. You can specify how many bins of how many tapes you want. In this slide, I wanted to show you that the cover point is not restricted to using only variables. You can have expressions on the sampling. So in this case, we have the cover point that it's actually sampling the data variable multiplied by 2. And also, another cool thing about the cover point is that you can also add a sampling condition. And this means that, okay, when I sample the cover point, I'll first check the condition. And if the condition evaluates to true, then I will register the data and I'll try to hit the bins. And of course, these are both evaluated at the point of sampling. So it's dynamically. So the cross is basically the same as a cover point, but it's a Cartesian product of the bins contained in the cover point. So if you have two cover points intended for covering, let's say, a bus, the data on a bus, and another cover point that is for the direction of the bus, then you cross them together. What you obtain would be a combination between what data we have seen and whether that axis represented the write or read. In this case, we have two cover points, which are defined as previous. This just shows us how to actually define a cross and instantiate it. And for that, you use the cross class parameterized by the types of data that have to match the cover points. and then you give it a name and the address of the cover points you are crossing. So the cover group is the final construct, which could contain multiple cover points or crosses. And the purpose is to have them all together relating to one feature. And the cover group is responsible for dispatching the sampling mechanism to the internal constructs. What this means is that I have been talking about how to sample the cover point and cross, but that actually is handled by the cover group. So when you have a cover group instantiated, you will be able to call the sample function that will trigger the data to get accessed by the cover points and crosses. And here it's an example of how to create one cover group. And for that, we have the cover group class defined in the library, and you have to extend that. Here we have an internal data that will be the point of sampling for the cover point. And then we have the macro, which is registering the cover group to the library. So you have to use this in order to define your cover group. Options. Options are used for adjusting distributions of different elements of the coverage model. And this means that you attribute different weights to different elements so that some of them matter more than others. And we can also disable and enable sampling collection during runtime. So you can disable the cover group, and then when you sample it, it doesn't register anything. You can also interrogate the database at runtime, as I already told you. And all this functionality is usable on all the coverage constructs except for bin. In this slide, I'll show you how to actually use it. And there are a couple of interesting points here. So first of all, we have an example of a cover group that is similar to the two slides before. And then we have a cover point contained in this cover group that it's also sampling on the variable data. And here it contains, the cover point contains two bins. And on the right side, we show how you instantiate the cover groups. You set the data on 0, and then you sample it. And what this happens to do is that it will trigger the cover group to register the data, and then we see the coverage number is 50, which is half, of course, because we have hit this bin, which is belonging to the only cover point. And then if we stop the sampling and set the data on 2 and attempt sampling of the cover group, which should have registered as a hit in this bin, which should have targeted the cover point and the cover group to reach 100%. This doesn't happen, as we can see here, because we have stopped sampling, of course. Then what you can do after you run your test cases is to actually visualize the coverage results. And for this, you have a tool included in the library, and it will show you the output as a table where the header is the cover group type, and then you have all the instances. In this case, we only have one. They are kind of nested, so we have the cover group instance, and then the cover point in that cover group instance, and under the cover point, each bin with the number of hits on the right side and whether our goal was reached or not. Then all the numbers get crunched up, and we get a nice overall average of the coverage. So in order to be able to do all that, you first need a coverage database. And to do that, you can use the function coverage save, which just exports the whole coverage model with all the options and the number of hits in each bin. Of course, this can be generated at any time during execution. One other tool which we have is the merging script, which can be used basically for when you have a regression with multiple runs, you need some way to merge the results together, and this is what we use. It's just a script which receives a top directory and searches for all the coverage databases, and then it will merge them together. We have another tool which was actually developed by one of the contributors to the GitHub repository. Special thanks to Armand Paiva for this. And it's a tool for reporting on a coverage database. So you get a coverage database, and you want to see the actual numbers without visualizing them through the GUI, through the web interface. You can use a script to dump you the data in some more user-friendly format so that you can process it. And this is the script for it. It's report.py. So as conclusions, functional coverage for SystemC brings us the notion of functional coverage from the System Verilog domain to the SystemC domain. And it also provides us with a metric that tells us what is the quality of the verification done. And it introduces coverage-driven verification as an alternative to the test-driven verification. And lastly, because the library is based on the System Verilog standard, it allows for an easy transition between System Verilog syntax and SystemC syntax. And it's easy to integrate into a regression flow because of all the tools that the library provides in the repository. Our roadmap includes stuff like default bins. We want to include this as soon as possible, so it's our top priority right now. And then we are looking at different aspects of SystemC integration, how to support coverage for custom data types that are needed for it to work with data types defined in the SystemC standard. And also event-based sampling so that we don't have to manually run the sample function. And maybe stuff related to cross-bin filtering. Although this is not yet certain, we are still investigating ways to go about it. But it's something that we are thinking about, and including transition coverage. This is a slide with references. If you would like to know about more details regarding functional coverage, you can look this up. To me, they seem to be pretty nice.
Concluding presentation, I will only pick a few slides. What you heard today, there are quite some working groups active in Accellera. I think the talks today on high-level synthesis primarily are being addressed in the synthesis working group. So if you have interest in understanding the synthesizable subset, what needs to be added, what are the challenges, I encourage you to join this working group. Mike also touched upon the data types, various data types, because of course data types need to be prepped for high-level synthesis, but there is also an impact if you want to run them into simulation. There is a trade-off to be made, and the data types working group is exploring the existing data types, new data types, and how that can be improved. The verification working group is currently working on what is called UVM for SystemC, and the functional coverage for SystemC presented by Dragos is also on the roadmap in this verification working group to offer that as a bundle. So if you want to do functional coverage in a UVM context using SystemC, UVM SystemC offers a reference implementation as well as a language reference manual that is still in draft mode. That team is also looking into the constrained random engine, which is a third-party library called Crave, which allows you to do the randomization. So UVM SystemC library plus the functional coverage library from AMIQ and this Crave library should offer you a compelling set of technologies to do functional coverage and randomization in the SystemC domain. I encourage you to have a discussion with your boss or with the group leader whether your company is a member of Accellera and whether it makes sense to join Accellera, and then you can join any of the working groups. We also run other events, the SystemC Evolution Day. We have organized that event for 3 years now in Europe. So it is a co-located event to DVCon Europe. It was quite successful. We had roughly 80 participants in October. And basically the objective of that session is to discuss what is necessary in the standard, additional features, what are the user experiences. So we had a quite diverse range of topics related to AMS, multi-language, and presentations are available on the Accellera website. And also this year, in October 2019, we are planning the next SystemC Evolution Day. And actually, we will also have a call for papers, a call for contributions. So we also encourage you, if you are doing something in the SystemC domain, which is not yet part of a standard, but which might become an interesting aspect to bring into standardization, feel free to submit that. I think the call will open in 1 or 2 months. Last but not least, the SystemC community is alive and kicking, very vibrant. I think you can find the community pages via this web link. And also in case you are new to SystemC or you have questions or remarks or concerns, feel free to raise your question to one of the Accellera forums. The SystemC forum is one of the most active forums Accellera is hosting with a lot of experts which can answer your questions. So I think it's worthwhile to check out whether your question has not already been answered on the forum. Otherwise, feel free to post this.